Hi everyone, welcome back to ChemHelp ASAP. Today we're going to be talking about the common ion effect. Let's get started. So the common ion effect is when we look at what happens to the solubility of a salt when the solution already contains one of the ions of the salt. So it might contain some of the cation or some of the anion of the salt. Let's take a look at a specific example. How does the solubility of calcium hydroxide change when it is dissolved in pure water versus when it is dissolved in a solution of 0.1 molar sodium hydroxide? And we're given the KSP value for calcium hydroxide. Because we are in equilibrium, I find it very helpful to use an ice table. So initially, of course, we have none of our cation or our anion. So what is our change here? This is going to be X and 2X. Remembering that this 2 comes from this 2 right here. So our equilibrium is going to give us X and 2X. So our KSP expression is just our calcium ion times our hydroxide ion squared. Don't forget that squared. Remember, you have a 2 in front of this hydroxide. Let's plug in these values here, and we're going to get X times 2X squared. We know our KSP value. It's given right here. So plugging in our KSP, that's going to be 4x cubed. So our solubility, or our value for x, is 6.9 times 10 to the negative third. All right, so that is our solubility in pure water. Let's see what happens when we dissolve this salt in our 0.1 molar sodium hydroxide. So what is the common ion here? The common ion is hydroxide. So again, we're going to need to set up an ice table, and it's going to look a little bit different. Initially, of course, we have no calcium cation, but initially we do have some hydroxide. Remember, we've got this 0.1 molar solution from our sodium hydroxide, so we're not starting with a 0 in our initial row. Our change is going to look exactly the same. It's going to be our X, it's going to be our 2X here, but our equilibrium looks different. Our calcium is just X, but our hydroxide is 0.1 plus 2X. Our KSP expression looks exactly the same, but we're going to be plugging in these equilibrium expressions. So that is going to be X and our 0.1 plus 2X. Don't forget your squared here. Now, this looks like it's going to be a bit of a bear to solve, and we're going to have a quadratic, and it's going to be a bit of a mess. However, our KSP value is very small. It is smaller than 10 to the negative third. So I'm going to assume that I can drop this plus 2x, that it's not going to make enough of a difference. If I do that, my KSP expression simplifies quite a bit. This is now much easier to solve. So plugging in for my KSP value, again, don't forget your squared here, I get an x of 1.3 times 10 to the negative fourth. Now let's double check my assumption up here that I can drop my plus 2x by using the 5% rule. Now the 5% rule says that my value of x over my initial concentration times 100% should be less than 5%. So for this calculation, here is my value for x. My initial concentration, of course, was 0.1 times 100%, and that gives me 0.13%, which, yes, is less than 5%. So my assumption is valid. Now finally, let's compare solubilities. So is our calcium hydroxide more or less soluble when we put it in 0.1 molar sodium hydroxide? Well, you can see here is my solubility in pure water, 6.9 times 10 to the negative third. Here is my solubility in sodium hydroxide, and it has actually decreased. And if you think about the fact that this is in equilibrium, if you have added product here, it's going to start to shift the equilibrium back to the reactants. Let's take a look at one more example. So how does the solubility of barium phosphate change when it is dissolved in pure water versus when it is dissolved in a solution of 0.35 molar barium chloride? And we are given the KSP of barium phosphate is 6 times 10 to the negative 39th. Let's first calculate the solubility of barium phosphate in pure water. Again, we need an ice table. So initially in pure water, of course, we've got no barium and we've got no phosphate. Our change is going to be 3x and 2x, and so our equilibrium is still going to be 3x and 2x. Here is our KSP expression for barium phosphate. Plugging in my equilibrium row, I get 3x, that is cubed, and 2x, and of course that is squared. I know my KSP, that was given in the problem, so here's my KSP, that is going to be times 108x to the fifth, And we have x equals 6.9 times 10 to the negative third. Okay, so that is our solubility in pure water. Let's check our solubility when we're dissolved in 0.35 molar barium chloride. Still setting up an ice table. Now, initially, we're going to have some of that barium. Remember that barium is coming from our barium chloride. That is the common ion. We don't have any phosphate though, so that is 0. Our change row is the same, our 3x plus our 2x, but of course our equilibrium row is going to be a little bit different because this is going to be 0.35 plus 3x, and our phosphate is just 2x. Our KSP expression stays the same. Don't forget this cubed or this squared. Again, I'm just going to plug these expressions in. So I get 0.350 plus 3x, again cubed, and 2x squared. Now don't panic yet because I'm going to use my assumption that I can drop this 3x. So getting rid of that 3x there is going to simplify my KSP. Here is my KSP that is simplified. Now this is going to be much easier to solve for x. So putting in my value for KSP, I get x equals 6.54 times 10 to the negative 20th. Before we compare, let's check my assumption, make sure it's valid. So we're still going to use the 5% rule here. I'm going to take my value of x over my initial concentration, this time my initial concentration of barium, times 100%, that should be less than 5%. So my value for x is 6.54 times 10 to the 20th. My initial concentration was 0.350 times 100%, and that gives me a percentage of 1.8 times 10 to the negative 17th. Yes, I would say that this is a valid assumption. Now that I know my assumption is valid and my value for x is correct, what does happen to the solubility of barium phosphate? Okay, so in pure water, here is our solubility, 6.9 times 10 to the negative third. And wow, you can see it went significantly down once we put it in that barium chloride. Again, if you think about your equilibrium here, if you're starting with some of the product, it's going to start to drive that reverse reaction. That is the common ion effect. I hope you found this video helpful, and thanks so much for watching.